Hello everybody, my name is Eduardo Sebastian and I'm gonna present LEMURS, not the animal. I'm gonna present Learning Distributed Multi-Robot Interaction, a paper conducted in collaboration between the University of Zaragoza and the University of California, San Diego. Multi-robot systems are one of the current challenges in robotics. We would like to have multi-robot systems due to their cooperation capability, which is a must if we want to address complex, highly coordinated tasks, such as this herding or this beautiful flocking. However, there are some issues that prevent the current use of multi-robot systems in this kind of tasks. The first is that it is hard to encode mathematically the objective or constraints of these tasks. Besides, the current analytical solutions are hard to scale with the number of robots. So our question in this paper is, can we find a control policy such that a team of robots with varying size achieves the goal of the task from just demonstrations? And yes, that's our goal. The goal of this paper is to learn scalable, distributed, continuous time control policies from just observed demonstrations of a certain task. To do so, we assume that we have a team of robots. We know the individual dynamics of those robots. The dynamics depends on the state and input of the particular robot. The robots interact in a distributed manner, which we describe by a communication graph, which is time varying and directed. And importantly, we define what we call Kahoot networks. They are basically the robots that are connected with each other by means of the powers of the corresponding adjacency matrix. So can we find a control policy pi parameterized by this theta depends only on the Kahoot networks of robot I, such that we accomplish the demonstrated task? We have a collection of demonstrated trajectories, as I said. So we would like to find the control policy that is optimal with respect to the difference between the learned and demonstrated trajectories. To do so, we propose LEMURS, which is an architecture composed by three main blocks. First is a Port-Hamiltonian dynamics model that restricts the control policies to those that are stable and distributed. So departing from the open loop dynamics, we propose a general input dynamic assignment passivity-based controller, which basically moves us from the open loop robot dynamics to the desired closed loop dynamics. So our purpose now shifts to learning directly the closed loop desired dynamics that are described by the demonstrated trajectories. So our purpose is to now learn this J matrix, the interconnection skew symmetric matrix, this R matrix, which is the dissipation positive semi-definite matrix, and the energy H. So our purpose now is to know how to compute these terms such that our controller is distributed and scales and respects the Port-Hamiltonian constraints. To do so, we go to the second main block, the self-attention model, which is capable of handling time-varying neighbors and team sizes. So the idea is the following. For each block, we have a network, a self-attention-based network. The output of this network, these three quantities, one per each network, must fulfill the Port-Hamiltonian constraints. To do so, we apply these local interaction operations, these ones, such that we achieve positive semi-definiteness of R, skew symmetry of J, and we find the partials of H by means of automatic differentiation. So we have always local interactions to handle time-varying neighbors and team sizes. And finally, the third block, to respect the continuous time robot dynamics, we use neural ordinary differential equations. So basically, departing from the initial state of the system, from the trajectories, we use an ODE solver to propagate forward and find a trajectory, this one. By building what is called an adjoint state, we can go backward through the ODE solver and find, again, the initial position of the trajectory and, importantly, the partials that we need to propagate and learn the architecture of the networks. So to evaluate our proposal, we have used 3 different tasks, collecting demonstrations, and we have seen the learned control policies derived from these demonstrations using just 4 robots. With 4 robots, we do it perfectly. But what is more important, we scale this with 12 robots or 64 robots, we still achieve the tasks. So, in conclusion, LEMURS can learn scalable, distributed, stable control policies from task demonstrations. Actually, we find that it's hard to encode some hard complex tasks from raw demonstrations. So we propose to try to learn them and do some kind of pre-processing to be able to address more complex tasks. Thank you very much for your attention, and please scan the code if you want more information about our paper. Bye-bye.